Thank you very much for inviting me, for introducing me. I'm currently as a lecturer at Barcelona School of Architecture, but today I'm going to present a work that I've been carrying out while at Brunel University and within the Annex 80, and along with other colleagues and members of the Annex 80 that are Agnese Salvati, Mamak Tutcaboni, Ian Gaur, yeah. And because we form the Weather Data Task Force of the Annex 80, and then I'm going to present the motivation and determination of worldwide future weather data and heat waves. So just an overview of the presentation. I'm going through quickly the purpose of these weather data sets that have been generated for the work of the Annex 80. And then I will explain how we have defined the methodology for generating such future weather data, how we have selected representative cities, a specific type of climate data, and a validation procedure of this climate data. And finally, I will present some results, so a comparison of the expected changes in some key variables, climate variables, in typical meteorological years of future periods compared to current periods. And just after me, after this presentation, Agnese Salvati will follow up with a presentation of the future heat waves that have been detected with the same methodology, and also some application of these weather data. So as already introduced by Peter, I just wanted to recall what are the basis and the motivation of the Annex 80. The Annex 80 resilient cooling of buildings is motivated by the fact that there is a huge increase of air conditioning and cooling demand in buildings worldwide. And this is quite concerning for its energy impact, environmental impact. And this is caused by both urban growth and climate change impact effects. So the Annex 80 intend to develop and assess different kind of cooling solution, resilient cooling solution that are able to withstand and prevent, on the one hand, thermal stress indoor in buildings indoors, but also reduce or minimize the building cooling demand and consumption. So to this aim, we needed a set of weather data basically to carry out building performance simulation and resilient assessment. And these weather data should have been representative of different climate zones worldwide, different periods, current and future periods, and also able to catch both the impact on the energy demand and future energy demand, cooling demand of buildings, and the possible impacts of climate change on thermal stress, heat stress. So the first question that in the weather data group of the Annex 80 we tried to answer was what kind of future weather data do we need it for carrying out this kind of assessment. So knowing that the changing climate will imply a change both in mean temperature, but also in the variance of temperature. On the one hand, we know that we will have warmer climates that have an impact on building cooling demand, but also we will have an increase of extreme events, extremely hot days, the heat waves that have the biggest impact on heat stress, and also risk for power outages. So we needed two kinds of weather file, one that is representative of typical meteorological years in the future, and another that is including the heat waves in the future period. And these kind of files were needed for different periods and different climate zones. And first, the second decision we also had to make was what kind of scenario we wanted to analyze, considering that the climate projections that are generated by climate models are based on possible future concentration of greenhouse gas in the atmosphere that are based on the IPCC assessment report. So we based the decision was based on the fifth assessment report that was the one available at the time and that is still available for climate projection. And we decided that in order to assess resilience of cooling solution, we had to analyze the worst case scenarios. So that's why we used a climate projection based on the RCP 8.5, that is the scenario assuming a business as usual approach that entails the maximum temperature increase at the end of the century. And also we had to select some representative periods in terms of climate. So we select three 20 years period in order to assess the impact of climate change, because 20 years is the minimum length of time that is needed to assess the climate change impact actually. So we selected, we compare the climate, let's say, in the historical period between 21 and 2020, and two future periods, one medium term around 2050 and one long term, which are the last 20 years of the century. And so once decided the scenario and the periods, we also had to design what kind of methodology to use in order to generate these variables. So basically, the climate projection are generated at the highest level by general circulation models that are numerical simulation with, let's say, a very coarse resolution. So they are run at the global level and they can have a spatial resolution of no more than 150 square kilometers. So, of course, this is not the resolution of data that is suitable for resilience assessment at the building scale. So, a downscaling of this data, of this climate projection is needed, and there are different approaches to do so. Let's say that there is a statistical downscaling that is also known as morphing method. That is a simplified way to modify observed weather data considering the future mean values estimated by these GCM models. But a more detailed approach is to actually perform a dynamical downscaling of these future weather data, which is based on the use of the so-called regional climate models, RCM models, that are forced with using boundary conditions from the global circulation models, and thus are able to provide a much more detailed distribution, spatial and temporal resolution of the climate variables in a regional domain. So these models are much more useful because, for instance, if we compare in this picture the estimated summer precipitation from global circulation model on the right and the regional climate model in the center of the picture, we can see that the regional climate model is actually able to estimate the variation in any variable, and so the extreme values that are expected in the future, while the global circulation model being approximated on a wider scale is not able to do so. And this is why we could not use morphing method or other methods except of the regional climate model to generate weather data representative of future extreme events like the heat waves. So this is really something that we wanted to do, even if it implied a more complex procedure to generate this weather data. But unfortunately, this is not the regional climate data are today available for a wide range of climate model combinations, socioeconomic projection worldwide through the Cordex project, which is the coordinated regional downscaling experiment that has been developed with the aim of coordinating this simulation and provide data exactly for impact assessment and adaptation studies. So we could access regional climate model projection for basically all the regions of the world, with the resolution that we expected to be at minimum 25 kilometer spatial resolution and 3-hour temporal frequency of the climate estimations, and for all the variables that are needed to then perform a building performance simulation. So not only air temperature, but also relative humidity, global horizontal irradiation, wind speed, and atmospheric pressure. So this is the main source of climate projections that we have used to generate the weather file. But also another important step in the methodology was to sort of correct the bias associated with model data. So the regional climate model data are a numerical simulation that can have a bias. And so we used historical observational data of ideally 20 years length, but at least 5 years, to compare, let's say, the performance of the regional climate model compared to the observation. So thanks to the observational data, we could correct the bias in the regional climate model data, both in historical and future period. So if you look at these two graphs, just to explain a bit more practically what does it mean. In the blue line are the distribution of air temperature on the left and wind speed on the right for London as estimated by the regional climate model for an historical period. But then the gray line was the actual distribution of the observed values of each variable. So after the bias correction, we could get to the red line that show a very good fit of the bias corrected regional climate model with observations. And so the same bias correction was applied also to the future periods in order to reduce any anomaly, let's say, in the climate estimates. So these procedures also assure a very the best quality that we could have also in future predictions that cannot be validated in another way. Okay, so once we have defined the methodology, we would like to apply it to some representative cities for the Annex 80. So what does it mean representative? That they would have covered all the climate zones that will be affected by climate change in terms of increasing cooling demand. So all the zones from 0 to at least 6, according to the ASHE classification. We just excluded the colder zone. And we also try to pick cities that are already with a high population or high population growth, where the increase in cooling demand will be more detrimental, let's say. And also we try to cover cities in different, we try to select cities in different continents, because even if they fall in the same climate zone, depending on the location, and we have seen from historical data that not all the continents have been interested by the same number of heat waves events. For instance, in this map, you can see that in the last 30 years, basically in Europe and Asia, there have been much more heat waves compared to America, Oceania, and Africa, for instance. So it was interesting to see what is the impact of climate change in different continents. And also then considering the people, all the people and the many institutions that have participated to this effort, we arrived to this final list of cities that do cover all the zones and many continents except Africa, for which we could not find observational data to perform the methodology completely, but we are really happy with the results. And so we use this set of 20 years hourly data of all the climate variables that have been bias corrected using observations to generate two types of weather files to perform simulation. The first one is the typical meteorological year, that is the standard weather file to generate, to perform building performance simulation, because it's a weather file that is constructed with a methodology that intend to select the best months. They are called the 12 months that are more representative of the climate over the 20-year period. So for each period, we generate a typical meteorological year. And then with another procedure based on the detection of heat waves based on relative temperature threshold, we also identified present and future heat waves and generated a weather file that include these extreme events. And more details will be given in the next presentation about this. But now I wanted to conclude presenting some results of this, of the weather file, and especially the comparison of the typical meteorological year. So what are the change in the main variables that we can expect in the future midterm and future long term in the different climate zones. So in this graph, you can see the change in temperature in the midterm in orange and in the long term in purple. And also you can see the comparison of the mean value from the 20-year data set and the mean value from the typical meteorological year. So that confirms that the typical meteorological year is actually representative of the 20-year period, because the values are very similar. And so this is a change in temperature, and you can see that the temperature is increasing in all the cities consistently in the future, and the increase is more pronounced, is higher in the long term than in the midterm. And there are some cities that are particularly affected, like São Paulo, Abu Dhabi, and Guayaquil, so cities in hot, dry, and hot, humid zones. Conversely, the change in relative humidity is not, it's quite variable. It depends on the cities. There are cities that show an increase in relative humidity, like Singapore, Guayaquil, Buenos Aires, Los Angeles, and Vancouver. And there are a couple of cities that instead show a significant decrease in relative humidity. And these are São Paulo, which is hot, humid, but also Abu Dhabi, which is extremely hot and dry, not humid. Another interesting result, instead, that was not probably very expected at the beginning, is the change in global solar irradiation, which is projected to decrease in most of the cities in both the medium-term and long-term future. And this result was at the beginning a bit, let's say that not all the models predict this reduction in global solar radiation, but it was found also in other studies. And in fact, it can be explained by a possible increase in aerosol concentration and cloudiness of the atmosphere that contribute to reflect solar radiation out of the atmosphere. So this was also another interesting result. And finally, the change in wind speed are let's say, less relevant in terms of energy impact. The city that seems to be more affected is Vancouver, that will experience a decrease of wind speed up to 0.7 meters per second on average. So just to finish, all these data are going to be published in a data paper, which is we are very close to submit for review, and will be available after review, after publication, for downloading directly from the Annex 80 webpage, and we will make available not only the weather file, but also the 20-year hourly data sets that are very useful also for other kind of assessment. And this has been possible thanks to the collaboration of basically almost all the institutions involved in the Annex 80, and with a very big of authors. And I'm very grateful for this. It was a very amazing experience being part of this project. These are some references about the methodology, but I will be happy to reply to any question at the end of the presentation. And so now I can leave the floor to Agnese Salvati, that will continue with her experience on heat waves.